Hi Science2 kiddos. This is the last part of Chapter 5 that I want to review using these slides, specifically Chapter 5.12 on elliptical orbits. I'll talk about what an elliptical orbit is, what geosynchronous orbit is, and escape velocity, and how hopefully you will and never should throw a baby or child high enough to achieve escape velocity, or else they're not going to come down. It sort of breaks that rule of, it's often said what goes up must come down. If you achieve escape velocity, that will not be the case. I'm going to test fire some poll everywhere questions for this when I lecture on this in class. But for now, you can try this on your own, pause the video, and see if you can get which answer it is. The question is, what is a satellite, or what are satellites? This is review from the previous parts of Chapter 5 that we went over. The correct answer should be this one. Any projectile moving fast enough to fall continuously around Earth. So there's that same definition for you right there. And remember that we have to be at least 150 kilometers above the Earth to get outside the atmosphere. That way there's no drag affecting the velocity of these satellite objects. They're not being slowed down or experiencing any friction from that. The minimum speed is 8 kilometers per second horizontally. That's what's going to keep a satellite rotating around the planet in a circular motion. This last part of the chapter takes us a step further and asks, okay, well, what happens if you go more than 8 kilometers per second? What if we are able to somehow launch our satellite projectile even faster? And if it's a little bit more than 8 kilometers per second, you're going to achieve what's called an elliptical orbit. And that's just referring to the shape of the orbit. It is an ellipse, which you can see here is sort of just a kind of a wider circle, and it has two what they call foci, or two focus points. And you could draw this. The way to think about this is, if you see this drawing over here, you could take tacks and put them down next to each other on a piece of paper and tie string or floss to them, and then have the pencil making tension on those strings and try to rotate it around. You would draw a wide circle like that. That is what an ellipse is, and that's what an elliptical orbit follows. And the reason why an elliptical orbit is shaped like this is because usually it's overshooting its mark, the satellite, right? It's going a little too fast, and then it has to kind of circle back. And so usually one of the focuses is the planet or the star that is being orbited. Next question is, how does the elliptical orbit affect the speed of the satellite as it travels? So again, you can pause this recording to try to answer this. The correct answer is that it's going to move faster as it approaches and passes the focus, and it's going to move slower as it gets further away. And so let's look into that. So satellites do not have an elliptical orbit. Their speed is not consistent throughout the trip. And so here again, as they get closer to the main focus where the gravitational force is strongest, they go a lot faster. They're sort of slingshotting around this source of gravitation, and as they get further and further away, the satellite slows down and sort of slowly makes its way back. It's almost like the gravitational field is sort of grabbing it, right? It's trying to escape, but no, it just brings it back and then it slingshots back around. And so it's constantly going faster, slower, faster, slower. And this gives the points different names. This isn't anything I'd expect you to remember. With the moon, you can see here on Earth, it would be going slowest at apogee and fastest at perigee when it's closest to Earth. And same thing with Earth rotating the sun. We're going fastest at what's called the perihelion and the slowest at the aphelion, I guess is how you say that. Last question to ask on this is, what do you think is geosynchronous orbit? So again, you can pause the video if you want. Think about that word. Just to break it down, right? Think of geo, what that means, and what synchronous means. To understand geosynchronous orbit, which I'll define in a second, satellites vary in the amount of time it takes them to rotate or orbit around the planet depending on their distance, right? Satellites that are very close to the Earth, as pictured here doing this polar orbit, they have to have a very, very fast horizontal speed to ensure that they continue to fall around the planet. In fact, it's literally a matter of hours that they can rotate all of Earth, right? They typically go around Earth every 90 minutes, which is a lot of rotations per day when you think about it. It only takes an hour and a half. But if you get further and further away from the Earth, a pretty significant distance, these satellites do experience a little bit less gravitational force, and therefore can have lower or less horizontal velocity and still stay in orbit. And it turns out, geosynchronous orbit refers to satellites that are 5.5 Earth radii away, which is the equivalent of 22,000 miles, which is a pretty significant distance, enough that the gravitational force exerted on these satellites by the Earth is going to be a little bit less. And so much so that they can actually circle the Earth every 24 hours and still stay in orbit. And hopefully that number looks familiar to you. 24 hours matches Earth's own rotation. And so this is referred to as geosynchronous orbit because it is literally synchronous, or the same, lined up with geo, the Earth, rotation. And so these satellites can stay literally above a single point on the planet at all times. They don't move. You could have a satellite above your head right now that just stays there, because everything's timed perfectly with how the satellite rotates and how Earth rotates. Now, there's a little bit of wobble, right? Earth does wobble on its axis, so this does get a little more complicated, but it's not something I want to dive into right now. Satellite TV, cell phones, things like that make use of geosynchronous orbits, right? They keep satellites up above certain areas, certain regions, and so service is given to all the people living in that area, right? There's a reason why everyone's TV satellites are pointed up to the sky. There's a satellite up there that's getting all those signals and sending signals back down to those satellites. Okay, so we've talked about circular orbits and elliptical orbits. The last thing we need to touch on is what's called escape speed, which I prefer to describe as escape velocity, right? Velocity takes direction into account, and when we say escape, we are moving away from the planet, away from the source of gravitation. And so it's exactly what it sounds like. It is the speed needed to escape the gravity of a planet or a star. On Earth, satellites have to be launched straight off the ground at least 11.2 kilometers per second or faster to get away from Earth's gravitational influence, right? If we manage to get something going that fast, it is not going to come back to Earth without turning itself around on its own. Earth's gravity will not be able to pull it back. It might start off looking like it's going to be an elliptical orbit, but then it will just keep going. The Sun, which is obviously much larger than Earth, even though it is further away, requires a much higher speed here on Earth. So even if we did get a projectile off of our planet Earth, it still has to also escape the influence of the Sun, which kind of shows you again how incredibly large and powerful the Sun is. But that requires 42.5 kilometers per second. And so humans have managed to do this. The Pioneer 10, which was a satellite that was launched back in 1972. It passed Mars. They did a little like slingshot thing past Jupiter, I think, to get it up to the adequate speed. But this little probe, pictured right here, has now left our solar system. And it is technically in interstellar space because it was able to achieve both escape velocities, the 11.2 kilometers per second to get off of Earth, and the 42.5 kilometers per second to get away from the Sun. And I'm sure it achieved the speeds needed to get away from all the other planets that it passed or got close to. Your textbook lists the escape speeds for different celestial bodies. The Sun, again, listed right there. You can see the 42.5 kilometers per second there. There's Earth. And kind of interesting to see the relationship between size and the required escape speed, which isn't that surprising, right? Because we know the more mass, the more gravitational force. The Sun is absolutely massive, and unimaginably so, and so it has a very strong gravitational force even at the distance that Earth is. Earth is kind of set as 1 here, and the Moon then has a very low escape speed requirement because it's so small. So in summary, I know there's a lot of numbers I threw at you, but I kind of like this diagram here because it shows you that, again, if you have at least that 8 kilometers per second launch at horizontal, you are going to achieve that circular rotation or orbit around the planet. If you go more than 8 kilometers, they don't show it here, but that would give you an elliptical orbit, so it would look more like this, where it slingshots out and then back in and then continues to do that. So it's still orbiting the planet, but just has sort of a wider circular motion. If you achieve 11.2 kilometers per second, that is escape velocity, and that's going to go shooting off on its own. That's for planet Earth. And then if you wanted that to continue going rather than going to the sun, you would have to somehow then accelerate to 42.5 kilometers per second. And again, though, I want to emphasize that all of these speeds are assuming that there's no air drag, that we are at least 150 kilometers up and out of the atmosphere, and that everything's acting in a horizontal direction and being launched off from there. Thank you.